Okay, we are back again. So, again we have come back to equation 13, right. Now, next that to maximize the function we will again take its natural logarithm, I told you, right. Therefore, maximize x, that is probability of z1 measure and z2 measure is nothing but maximize x, that will be minus ln sigma 1 root 2 pi minus z1 measure minus x upon r1 whole square, then minus ln sigma 2 root 2 pi minus z2 measure minus x upon r2 whole square divided by 2 sigma 2 square. That means that your what you will take, that this two PDF function you will take, this one and this one, and then you take its natural logarithm product actually. So, ultimately all will be, this one will be minus of sigma 1 root 2 pi, this one will be minus of sigma 2 root 2 pi ln, that minus of ln sigma 1 root 2 pi, then minus of ln your what you call z1 measure minus x upon r1 whole square upon 2 sigma square, then minus of ln sigma 2 root 2 pi, then minus your what you call, it will be z2 measure minus x upon r2 whole square upon 2 sigma 2 square, because you take just product and you take natural logarithm, right. So, it will come like this. So, this term and this term is constant and same as before, right. We want to maximize x. So, one minus sign is before this term, minus sign is before this term, then this term will be added and we will minimize this term such that we will get the x estimated value, right. Therefore, this the minimum sort is found, right. That means you minimize x, that means this is this two term I told you before also for single ammeter case. So, in this case you minimize x, that is minimize this function for which you will get the estimated value of the x. So, z1 measure minus x upon r1 whole square upon 2 sigma 1 square plus z2 measure minus x upon r2 whole square upon 2 sigma 2 square, right. So, now the minimum you will get if you put d dx is equal to 0, d dx of this term is equal to 0. If you do so and take the derivative, that 2 term anyway right hand side is 0, will not be there. So, minus of z1 measure minus x upon r1 divided by r1 sigma 1 square minus z2 measure minus x upon r2 divided by r2 sigma square is equal to 0, right. And then from where you solve x is equal to x estimated. So, if you solve this one, hold on. So, if you just hold on. Now, if you solve this, then you will get x is equal to x estimated is equal to your z1 measure upon r1 sigma 1 square plus z2 measure upon r2 sigma 2 square. This way we have written plus divided by your 1 upon r1 square sigma 1 square plus 1 upon r2 square sigma 2 square. This is equation 15. You can easily write it from that equation, just simplify. I did not write intermediate step, but this is the expression. If one of the ammeters is of superior quality, its variance will be much smaller than that of the other meter. For example, if one superior instrument means its sigma, the standard deviation will be very low, that means the variance also will be low, right. So, then that for then that of the other meter, for example, if sigma 2 square is your what you call much less than sigma 1 square, right. Therefore, we can that means that ammeter 2 is a superior quality than sigma your ammeter 1, because its standard deviation is much less than your what you call this standard deviation of your what you call that your ammeter 1. So, here you have taken the variance also, variance sigma 2 square, variance also will be much smaller compared to your what you call the other meter variance sigma 1. Say this is something like this, we assume, right. Then what will happen, that x is equal to x estimated you can write from this equation only, from equation 15 only, just simplify from this equation 15 only, right. You can write x is equal to x estimated is equal to r2 sigma 2 square z1 measure plus r1 sigma 1 square z2 measure divided by r2 square sigma 2 square plus r1 square sigma 1 square into r1 r2, right. Now, if you look into that, if sigma 1 square is much your greater than your what you call sigma 2 square, in other way that sigma 2 square is much lower than sigma 1 square, right, then you can just what you call that what you will get, that in that case you neglect neglect this your what you call that sigma 2, because sigma 2 is your what you call sigma 2 square is your very small compared to sigma 1 square. So, if you neglect this term, that your if you neglect this term, for example, just for our say your analysis. So, this term should not be there, this term should not be there, then this term should be there. So, it will be r 1 sigma 1 square by r 1 square sigma 1 square into this term r 1 r 2, right. So, in that case what will happen, sigma 1 square and into z measure into z 2 measure, right, and r 1 and r 1 square. So, this one will be cancelled, ultimately it will remain as z 2 measure into r 2, right. Therefore, x is equal to x estimated, you will get z 2 measure into r 2, it is a assumption. Otherwise that you, when you have 2 meters and you have different measurement, from that you can see that x estimated value, it is not like a first case where we took only 1 meter and 1 voltmeter. So, everything is related to other. So, you will get the best estimation of the voltage, right. X estimate, x is nothing but your voltage, right. So, thus we see that maximum likelihood method of estimating our unknown parameter gives us a way to weight the measurements properly according to their quality. That means, it depends on sigma 1 and sigma 2, that standard deviation. In other way, it is variance, in this case expression it is coming all sigma 1 square sigma 2 square, it is variance, right. Now, that is actually whatever we see for 2 ammeters. Now, come to little bit much deeper. So, now in this case what we will do, that if we are estimating a single parameter x using nm measurement, we would write the expression. I mean, you have nm number of measurement, right. I mean, m stands for measurement. So, in that case you have to say minimize x, function is given jx, right. So, say I is equal to 1 to nm, z I measure, that is the ith state variable, minus f I x, right, and sigma I square, and you are right. So, this thing actually we have taken z I measured minus f I x square whole square, this z I measure minus f I x whole square divided by sigma I square, right. So, in that case this function we have taken, and we are a single parameter in nm measurement. Suppose you have different measurement devices and measuring, but you know the standard deviation. So, a divided by your sigma I 1 square is given, right. So, this is a question to you, that I should have taken also z I measure minus f I x whole square instead of divided by sigma I square, right, that variance. So, but we have divided it by sigma I square. Why? This is a question to you, that why this function is divided by, answer is very simple, but why this function is divided by your what you call that your just a your what you call that sigma I square. I should have not have given that one also, I should have taken simply the squared error, right, but we have divided it by sigma I square. So, this is a question to you, that why, what is the reason, right. Now, where you will find just hold on, where you will find that f I actually is function that is used to calculate the value being measured by the ith measurement, right. We will see that what is f I, and sigma I square variance for the ith measurement. So, this function you have to your what you call, you have to minimize. So, this way we have taken, and you have nm number of measurements. Now, jx is equal to the measurement residual, because we are taking measured value, actually this is measured value, and this one you are calculating actually f I x. The way in the load flow studies you have seen, no, that for convergence p I minus p I schedule, then q I minus q I schedule, the schedule value is there, but p I and q I you are computing through your algorithm, that is your through your mathematical expression, right. So, and you are trying to minimize, or what you call minimize that error such that it will be equal, and then you are just trying to your what you call checking the convergence. So, here also z I measure minus f I x basically nothing but the residual. So, that is measurement residual, and nm is number of independent measurement, right. So, and z I measure is equal to ith measured quantity, right. So, this is the nomenclature. Now, note that equation 16 may be expressed in per unit or in physical unit such as megawatt, megavar or kV. I mean, this unit z I measure or f I or sigma, you can take it in per unit or in real quantities like megawatt, megavar like this, or voltage, right, kV. So, now suppose if we were to try to estimate ns unknown parameters using nm measurement, suppose we have ns number of state variable, right. Suppose we have ns number of state variable, right, and we have nm number of measurement. So, generally we can find three things. One is when ns greater than nm, right, when ns number of state variable is equal to number of this thing, another is when ns less than nm, right. All the three cases are there. So, we will see that. So, here we have, suppose we have ns number of parameters, that is state variables, using nm measurement, right. We would write that you minimize your x1, x2, x2 up to ns, that is x ns means it is number of state variable, right. That is your j is function of x1, x2 up to x ns, and number of measurement I is equal to 1 to nm z I measured minus f I also function of your x1, x2 up to ns, and this is whole square, right, divided by your sigma I square. So, you have to minimize this function when f is a function of your n all the state variable, that is ns number of state variables, and you have nm number of measurement, right. So, the estimation calculation of equation 16 and 17, right. So, the equation 16 we have seen, this is equation 16, and then equation 17, right, is known as a weighted least square estimator, right. So, actually it is called that your weighted least square estimators, right. So, again there is a question why it is divided by sigma I square. So, now matrix formulation, that how we will do this. If the function say f I, it is function x1, x2 up to ns, that is number of state variables, a linear function, generally whatever we are trying to do it, first we will assume that f I is a linear function of all the state variables. In general, AC circuit also we will see later, when you come to the AC circuit, that your power function, power injection and other things are not linear, it is a non-linear, right. So, that will be seen later. First let us see that f I, that function of x1, x2, ns are linear function, that is equation 17, it has a closed form solution. Let us write the function that f I x1, x2 up to x ns, that number of state variables. Therefore, that f I x1, x2 up to x ns is equal to, you can write f I x, right, is equal to, you can write say h I 1 x1 plus h I 2 x2 plus up to h I ns x ns, right. So, this is actually equation of x I, it is a linearly related, right, say it is a linear function. In AC circuit it is not, right, because sine cosine terms are involved. So, therefore, then if we place all the f I function in a vector, then we can write this one f x is equal to f 1 x, f 2 x, you have up to nm number of measurement, that f nm x, that is equal to h into x, because you have this f I, whatever you write, that I is equal to 1, 2 up to your nm number of measurement. So, it is h I 1 x 1, h I 2 x 2 up to h I ns. So, these are into x ns number of state variable, and this I actually is equal to 1 to nm, that is your number of measurements, right. That is why this f x can be written as f 1 x, f 2 x, because x is nothing but your, it is a vector x 1 x 2 up to x ns, right, and up to f n m, the number of measurement x is equal to h into x. So, this is a matrix actually, h is a matrix. Here I have put in like this in bracket h. In your next video lectures, instead of avoiding all the time writing bracket, simply I might have written h x, right. So, meaning is same, this h and your bracket h both are same, right. Similarly, other matrices also same. So, that means this h matrix, right, this h matrix actually it will be nm into ns matrix, because you have nm number of measurement and ns number of state variables, right. So, it is nm is equal to number of measurement and ns is number of unknown parameters being estimated, that is actually nothing but the state variables, right. Therefore, placing the measurement in a vector, so z measure is nothing but z1 measure, z2 measure up to jnm measure, this is jnm measure, that is equation 20, right. So, that means this is also putting it in a vector form hx form, and this z also we are putting like this z measure, right. we may then write equation 17 in a very compact form, that is your minima, because it is a, if you go to equation 17, right, if you go to equation 17, it is a quadratic function, z I measure minus f I of x 1 x 2 x n s whole square divided by sigma I square. It is basically your what you call is a quadratic function, and you have ns number of state variables and nm number of measurement. That means mathematically sorry, mathematically we can write this equation that your minimize x, right, you have to find out x value, j x is equal to, you minimize j x, that is z measure minus f x transpose, right, then into r inverse your z measure minus f x. So, this quadratic function can be written like this, because this matrix R we are writing is R matrix. The matrix R actually, what is matrix R? If you come here, this is actually you are putting, right, that sigma I square, it is sigma I square. So, basically making it here, later it is given that what is 1 upon sigma I square. So, R actually it will be a diagonal matrix 1 upon sigma 1 square, 1 upon sigma 2 square, right, up to like this, and this is 0, this is 0, right. Now, if you take R inverse, the inverse of this matrix, it will be nothing but your sigma 1 square, sigma 2 square, like this it will come, this is 0, this is 0, right. So, that is why that actually so many state variables are there, that is why you have made it in that matrix form, diagonal matrix, right. So, that is why it is z measure minus f x transpose R inverse, right, z measure minus R inverse into z measure minus f x. And another thing is that your f x is equal to your, here I am putting it, because later I have written directly that f x is equal to say h x, right. Then when you will take the transpose, z measure transpose minus f x transpose. So, f x transpose actually it will be x transpose h transpose, right. So, you put all these things and then multiply, the way you multiply, but note that it is this, all this is a vector, right, it is a matrix, right. So, when you multiply that your z measure minus f x is equal to h into x, right, all these things will multiply carefully, do not write the way we make a minus b into a plus 2b, not like that, right. So, just go for this multiplication. So, I will not show this one, but directly I will write, I think it is understandable for you, right. So, when you multiply, and R I told you that R actually I told you that this is I later stage I did not put in brackets, simply I have written R. So, R is equal to actually I told you that your this is actually this one actually it is R inverse, right. So, R actually 1 upon sigma 1 square, 1 upon sigma 2 square up to 1 upon sigma n m square, right. And your R is called the covariance matrix of the this thing, and it is 1 upon c, and this is 0, this is 0. If you take R inverse, then only it will be sigma 1 square, sigma 2 square up to sigma n m square, right. So, that is why here it is actually it is R inverse, right. So, this is corrected. Now, R is called the covariance matrix of the measurement error, right. To obtain the general expression for the minimum, that is expand the expression, and if you expand the expression you will get your what you call just 1 minute, this is R inverse, just 1 minute, this is R inverse is equal to sigma, no, it is correct, just hold on. R is equal to, we have taken say sigma 1, sigma 2, sigma 2 square. So, we are writing R inverse, say it is actually 1 upon sigma 1 square, 1 upon sigma 2 square up to sigma n m square, this is 0, this is 0. So, this is actually R is equal to, you have taken, this is called the covariance matrix of measurement error, right. So, here we have taken like this. So, therefore, this when you multiply all these terms, when you multiply all these things, so it is z measure terms R inverse z measure minus your z measure transpose R inverse z measure minus x transpose H transpose R inverse z measure minus z measure transpose R inverse H into x plus x transpose H transpose R inverse into H into x. So, everywhere I have put it in bracket. Later I have removed the bracket such that it will save the space, but understandable that it is a matrix, right. So, in this case the minimum of j x is found, right. So, whatever we will do, that minimum of j x that you have to take that your what you call the del j x upon del x is equal to 0. This is equation 22. So, you have to we substitute that f x is equal to h x, you have substituted, and then we got this thing. Now, minimum will come when your del j x upon del x I is equal to 0 for I is equal to 1 to n s number of state variable, right. Therefore, if you take the derivative, this is nothing but called the gradient, right, and we have to make it exactly delta j x, gradient of j x is exactly 0. If you take the derivative with respect to x, it will come like this, that gradient of j x will be minus 2 into H transpose R inverse Z measured plus 2 H transpose R inverse H into x is equal to 0, right. And if you solve it, 2 will be cancelled, you solve it, you will get x estimated is equal to H transpose R inverse H whole inverse, then H transpose R inverse Z measured. This is equation 23, right. So, equation 23 holds when n s less than n m, that is over determined case, when number of state variables are less than number of measurement. When number of measurement is more than number of state variable, it is called over determined case, and when n s is equal to n m completely determined, it will become x estimated to h inverse. If time permits, this completely determined case I will derive at the end if time permits. And another thing is that under determined case, in this case n m less than n s or n s greater than n m, that also derivation if time permits we will see that. But for this till now we will only consider the over determined case. So, what happened that later stage all this matrix whatever you have H, R and this thing, I did not put in that your bracket, simply what I will write, for example, this example that x estimated, simply we write that H R inverse H whole inverse, right, then your H transpose, then R inverse, then J overwriting on it Z measure, this way we will write, right. So, again and again we will not put it in bracket. So, if you just take the derivative and it is a quadratic function, right. So, definitely you will get the solution of this one. So, this is actually possible if f x is equal to h x, I mean it is linearly dependent, right. So, and this one your what you call this H whatever we will study now, that over determined case, they are completely determined and under determined case, if time permits we will derive that, right. Now, consider that your what you call example of weighted least square state estimation. Now, suppose meter full scale value is 100 megawatt. So, meter accuracy is plus minus your 3 megawatt, that is 3 sigma is equal to plus minus 3. So, 3 sigma is equal to 3. So, sigma is equal to 1 megawatt, and you take 100 megawatt full scale value. So, in per unit it will be 1 upon 100. So, 0.01 sigma will be 0.01, right. Now, that same example, same data, that power flow, that is 1 to 2, that is f12, that x12 value earlier we have taken. We are not going back to the diagram. So, already 2-3 times we have seen the diagram, right. So, it is 1 upon x12 delta 1 minus delta 2. This is actually 5 delta 1 minus 5 delta 2. Similarly, power flowing in line 1-3, that is P13, this is nothing but your F13. There in the mathematics it was Fi or what you call F1, F2 up to Fnm, right. But when you are solving the problem, actually it is F1 to F13. That means if you define like this, that my F12 actually it is line 1, that is F1. If my F13 you define line 2, that is my F2. If F32 you define line 3, F3. So, it is 1, 2, 3. So, right, this is basically 1, 2, 3. So, that in the mathematics it was F5, but here it is when coming to the problem, it is line 1 to 2, 1 to 3 and 3 to 2. So, we make F12 is F1, F2 is F3 or what you call F13 is F2 and F32 is F3. So, your understanding actually there will be no confusion, actually no confusion. Only thing is that regarding that R, initially I saw it is R actually, but it was R inverse, right. So, that is why, so everything, all the notes, everything is correct to the best of my knowledge, right, everything is correct. So, question is that your similarly F13 is 1 upon 0.4 delta 1 minus delta 3, but delta 3 is a slack bus. So, it is, so delta 3 is 0. So, it is 2.5 delta 1, and F32, that is nothing but F3, that is P32, it is 1 upon 0.25, because x32 0.25, x13 0.14, initially all these parameters we took, and it is actually delta 30, so it will be minus 4 delta 2. So, this sigma actually 1 upon 100, because meter accuracy, if you look into the meter, ammeter, voltmeter, another thing, this meter accuracy will be given say plus minus 3%, something is given. If it is given in percent, that means it is in per unit. But if the meter's full scale value is 100 megawatt, and if it is given plus minus 3 megawatt, that means basically 3 sigma is equal to 3 plus minus, but we will take only your what you call that your sigma is equal to 1, because our case that sigma square will come, right. So, basically it is 0.01 in per unit, and the bus 3 was a slack bus. So, delta 3 was 0.0, in this equation delta 3 is 0.0. So, we get that matrix, H matrix we have to get. So, actually that means if you write like this, your x estimated actually nothing but your delta estimated, right. So, delta estimated is equal to actually delta estimated 1 is delta 1 estimated and delta 2 estimated, right. So, that is why if you form this equation that your this thing, then your H actually will become this matrix, this is your H matrix, right. So, if you see that it is 3 into 2 matrix, that is nothing but your Nm into Ns, because your number of measurement is 3, because all the 3 lines measured value was given, but number of state variables actually it is 2, right. So, that means your what you call, that is why this matrix H matrix is 3 into 2. And another thing, I have missed one equation number in this note, that x estimated is nothing but your delta 1 estimated and delta 2 estimated, right. It is somewhere this equation number, I think it will be 27 somewhere, right. So, that is why the sigma 1 2 sigma 1 3 are all the meters that same sigma, same standard your deviation. So, their variance actually sigma 1 2 square, sigma 1 3 square, sigma 3 2 square is nothing but your 1 upon 100, I told you 0.0001, right, it is 0.0001. So, basically from it is a mathematics whatever derived, basically sigma 1 is equal to sigma 1 2, sigma 2 is equal to sigma your 1 3, and sigma 3 is equal to sigma 3 2, right. Therefore, your this is my r is equal to this one sigma 1 2 square, sigma 3 2 square, all other elements are 0, and z measure already earlier it was given same data. So, it is actually 0.62, 0.06 and 0.37, right. And next that is delta 1 estimated and delta 2 estimated, right. I told you that will be equation 27. So, this is if you look into that, this is my H transpose, right. This is my H transpose, this is my R inverse, this is inverse, and this is my H, right. And this is again if you look into that, this is my H transpose, this is R inverse is given, and this is Z measure, right. So, everything is multiplied. So, just put every value, just you put every value in that expression, that is your in this expression. I will go back to that, just hold on, just hold on here. You go back to this expression, this equation your equation 23, you go to this expression, right, equation 23, right. So, what you will see that this is equation your 28, I told you, after 27 28 has come, and I told you that 27 that x delta 1 estimated, delta 2 estimated, and if you put all these values here in this expression. So, if you just put it, it is H transpose R inverse H whole inverse, then it is again your H transpose R inverse, then it your whatever is coming that Z measure is given, just put everything value and you just simplify, then you will what you will get this inside this matrix, it will be 2 into 2 only. So, it is manageable because it is a diagonal matrix, it is a diagonal matrix, all other elements will be 0, right. So, it is easy to multiply and get the result, right, and in calculator 2 into 2 3 into 3 matrix inversion easily will get it, and if you do so, you will get delta 1 estimated and delta 2 estimated. Delta 1 estimated is 0.0285 radian, and delta 2 estimated you will get minus 0.09428 radian, right. and based on this estimated value you will get P12 is equal to 61.4 megawatt, P13 you will get 7.1 megawatt and P32 you will get 37.7 megawatt, and Pg1 if you calculate 68.5 megawatt, Pg3 30.6 megawatt, PL is equal to 99.1 megawatt. So, from this example you can see that we have used all the 3 state variables, right. We have used all the 3 state variables, and based on that 3 state variables we have computed delta 1 and delta 2 estimated values. Based on that, this result we have got P12 power flows in line 1 2, 1 3 and 3 2, and earlier we have given example that only 2 reading and third reading is redundant, but in this case we have used all the 3 readings and this is the best values, right. So, thank you very much, we will be back again.